morning. It is a real pleasure for me to be here, and I would say even a huge honor that I am able to share my experiences with all of you. And if I may use an Indian word, it's my bhagyam, I will say, to be here specifically because I'll share a secret. I was born less than 2 miles from this venue. So for me, it is a huge, huge honor to be here, and I'm so glad. I thank Target for giving me this opportunity to speak to all of you. And what I'd like to share with you as I talk about some of the innovations in optimization, it'll be blended through in some way through my analytics journey, through my career. So I started with a PhD in operations research as an individual contributor at SAS Institute, which is a major software company in the United States. And through the years, I grew in leadership opportunities to become the leader of the OR department, and then I became the leader of the advanced analytics R&D at SAS. And in that process, something I realized was that optimization can play a huge role in almost every one of the analytical and data sciences fields that we are familiar with, and also a lot of opportunities in AI. So I'll share with you some of these experiences and then talk specifically about an optimization problem specific to retail. So throughout this process, the questions that always come up, and as you grow in leadership opportunities, something to remember is how can I make a difference to my team, to my company, and so on. And for me specifically, I was always looking to see where can OR or optimization add value to the business problems. And what are the customer priorities? What are their business problems that need to be solved? And if you keep that in mind, you can keep innovating. And throughout all of this, something that I focused on a lot in my multidisciplinary team was getting everybody to work together in an interdisciplinary manner to make advances in optimization, analytics, and so on. If you think about the different types of techniques that one uses to solve some of the global problems, you can see some of the descriptive analytics are where you're looking at what happened in the past, why did something happen, etc. Then if you go to prescriptive analytics, you're looking at what is it that the current data and what you have seen in the past can tell you about the future in terms of data mining, forecasting, etc. And having all of this information, of course, you want to solve the business problem, which is always optimizing something. You want to either minimize cost or maximize the profit. And through all of it, there are a lot of OR techniques that come into play. So you can see how all these techniques come together to actually help you solve the business problems, whether they be in retail, finance, or hospitality, or you name it, medical fields as well. And at the end of it, all you're trying to do is you've got data, the volumes keep growing, and you're applying various analytical techniques to get value, because without being able to get value from that data is just a bunch of numbers or images that are not of no use to anybody. And over the years, over the decades, the data volumes continue to grow, which also made it more and more important that we should be able to solve for these problems as data volumes grew in immense numbers. The business needs also mandated huge performance improvement. For instance, when you're doing predictive modeling and trying to do forecasting, demand forecasts, for instance, you know that the demand changes depending on the season, it changes depending on the location. The demand in Kashmir will be different from the demand in Chennai, for instance, when you're looking at even clothes, for instance, right? So you need to know segment all these populations according to the region and then build models. And while you're building models, you know, if you've done any data mining or machine learning, you'll know that the best model is one where you have gone through multiple different analytical techniques, be it decision trees, gradient boosting algorithms, neural networks, whatever the case may be. You're looking at all these techniques and finding the best parameter that helps you solve the model and find the best model to suit the data. So you need to do microsegmentation, which is breaking all the population into different segments. You need lots and lots of models that need to be built to pick the best model, and so on. So you can see that you need always to have highly performant algorithms. So the business need and performance improvement needs increases with the number of segments that you want to make and the number of models that you want to try. And you can see, for example, I talked about demand forecasting when you're trying to predict, even recently during the pandemic, we were trying to predict where the next wave would come, in which part, in what form, etc. We've seen all of that, and that has become common knowledge. And when you have so many models to build, you need automation. Automation so that you don't need to have a group of people sitting and running through all these models, all these parameters. You need the machine to be able to do all of this more automatically, pick the best model automatically. And as you apply all these analytical techniques in multiple ways and automating things, we get more and more into the world of AI, where it almost seems like magic, like we just heard. So in all of these stages, the main goal is you want to decrease the latency and get results as quickly as possible. So through the years, I found that interdisciplinary innovation had many, many opportunities for using optimization. In statistics and machine learning, for instance, these are some of the techniques that I've listed on this slide, where they're generic. When I say generic, I mean they can be applied to many different types of problems in different types of industries. So one particular type, support vector machines, can be applied to many different industries, many different problems, or quantile regression, and so on and so forth. And in each one of these, there are various optimization techniques that get used. The other type of innovation we needed to do was for some specific business problems where a generic way of solving it was not good enough. You really needed to understand the business problem and build custom models. So the examples that I've given on the right-hand side are, for instance, optimal binning for credit scoring. We needed some customized algorithms. Propensity score matching needed some graph algorithms, and reinforcement learning, which we hear a lot about in AI, is nothing but partially observable Markov decision processes that the OR folks are very familiar with. So combining all of these, we saw that this is really a wonderful area. So when I talk to young students who are just starting in data science, I tell them that the world is ahead for you. There are lots of opportunities. You can think of it as a golden era for AI, machine learning, and data science, because there is data, there is a huge computing power which we could not have imagined ever at all, and lots of algorithms that are being innovated. So using all of these, you are really in a wonderful space right now. So these are all different individual techniques that I've talked about. But when you look at a specific business problem, specifically in retail, for instance, when you're looking at price optimization, clearance optimization, and so on, there are multiple techniques that need to come into play. You first need to do demand forecasting, then you need to build some statistical or machine learning models, and then need to figure out what the objectives are, and then decide what type of optimization techniques to use. So it's almost like a puzzle that you need to put together, taking these individual techniques and building the entire solution to go from data all the way to the result that you can then implement. So I always like to say the whole is bigger than the sum of its parts. It's almost like saying 2 + 2 need not equal 4. You can actually get more than 4 by putting all of these things together. So business solutions in multiple domains we worked on, like credit risk optimization, marketing optimization, revenue optimization in hospitality, and many of these other optimization solutions. Today, I'd like to share with you a little bit more detail about a specific problem in the retail industry, namely size optimization. And let me explain what I mean by that. So if you're talking about buying shirts, if you're talking about stocking shirts or shoe sizes or shoes in a store, you need to match the demand to the sizes that you keep in the store, right? Obviously. So essentially, what does size optimization really mean? And what are the challenges for size optimization? The demand, like I mentioned, varies by size, by region, by the store location even. And what happens if you don't have the right number of inventory items for the demand that you foresee at that particular store? You could either have too much of the inventory, which means at the end of the day you have size 15 shirts or size whatever shirts hanging around because they did not get sold. And so you have to either do a clearance or markdown optimization at the end of the season, or you might run out of the shirts that you need of a particular kind. And what does that cost? It costs unhappy customers because they'll go away. And not only did they not get the shirt they want, but they did not buy everything else that they could have bought while they are in the store. So lost sales or excess inventory is one of the challenge when you don't match the size to the demand, etc. In addition to that, when you're talking about specifically shirts, because that's the example pictures I have, when you're talking about shirts, the vendor or the manufacturer, which is shipping the shirts to you, has different sizes that are packaged in pre-packs, in packages that they decide. So they might include some small, medium, large, or 15 smalls and 16 mediums, etc., in pre-configured packs. So when you have these vendor-imposed pack configurations, then the question is, how do you match your demand to the packs that the vendor is going to provide, and how do you optimize that? So if you do it correctly, you can address a lot of inefficiencies in many different ways. So the solution actually requires two different components. One is size profiling, and the other one is pack optimization. Size profiling, essentially, is where you're trying to get the demand forecasts and use that to figure out the profiles for a particular type of size, the different sizes in a particular store location, etc. And the methods that are used in this size profiling solution are clustering, first of all, to group like stores together and like demand forecasts and create the size profiles. Demand forecasting. Another problem in many of these problems is how do you estimate unconstrained demand? So if you run out of shirts, you know that you've sold 50 shirts, so sure, the demand was at least 50, but you don't know if maybe the demand could have been 100, it could have been 55. So trying to estimate that unconstrained demand is a very difficult imputation problem, and so you need to do some imputation to estimate the unconstrained demand. So these are all various different statistical and modeling techniques so that you can figure out what the sizing plans need to be to optimized to meet the demand. So that's basically the problem of size profiling. Demand forecasting is obviously a key part of size profiling. Most forecasting techniques, most forecasting methods use constrained optimization of the form. Most of it is a quadratic form where you're minimizing a quadratic expression or maximizing some other expression subject to certain constraints. So most forecasting methods are like that. So usually the loss function is a quadratic term, and then in order to do that, you need to be able to apply some quadratic optimization techniques to solve this problem. In particular, in retail, what we had to do when we were looking at markdown optimization or regular price optimization, there is an additional problem where you could have hierarchical forecasting. And by that I mean the different sizes or the different types can fit into different styles, subclass, etc. So there is a grouping or a hierarchy of the different types of merchandise or products that you could have. And the problem is, at what level do you forecast? And do you aggregate or disaggregate, depending on whether you're at the middle or at the top or at the bottom? Sometimes it might be that you have enough data, you have the right data so that you can forecast at 2 different levels or more levels. And if you do that, you have to reconcile them, because it could be that you've got forecasts at level n and another set of forecasts at level n plus 1, but then the level n plus 1 forecast, if you sum up the ones at n, should kind of match that, right? Otherwise, there is a mismatch. So how do you get or reconcile these forecasts in the minimum way so that there is minimum difference between one level versus another? That's what we mean by hierarchical forecasting. That obviously imposes additional constraints. And this was a huge optimization problem with lots of quadratic constraints and quadratic objective function. So this was a wonderful problem for our teams to sit down and solve together. And we used an iterative interior point method algorithm to solve this constrained quadratic optimization problem. And of course, the challenges increase as the volumes of data that you're dealing with continue to grow. So this is just one part where we talked about the size profiling. Next, I come to the next phase, the second phase of this problem, which is pack optimization or pre-pack optimization. Like I mentioned, the manufacturers might have different types of packs that are pre-configured, and that's what they would ship to the distribution center or directly to the stores. And you could have an outer pack in this particular case. The outer pack has a total of 24 items, where each of the outer packs contains 4 inner packs, and each inner pack has 6 items. So that's how you get a total of 24 items. And within each inner pack, it could be multiple SKUs or a single SKU. So now, again, you can see if you're trying to if you have a size profile of what you need for your particular store, how do you say which packs you need to order? How do you get that? So that is basically, in simple terms, that is the problem. So the business constraints are, you want to determine the order quantities of packs that best match your size profile. You want to meet the size level demand so that you have the right. So you might order some packs which are all single SKUs, another set of packs which are multiple SKUs. But how do you do this matching? So it actually becomes a huge, huge optimization problem. And in addition, there's a question of if there's a distribution center where the packs are being shipped and then going to the store, there may be the problem that at the distribution center, some of these packs have to be split apart and then shipped to the stores. Now, if you do that, there's an additional labor cost. So you don't want to have too many packs that need to be split. So now you have multiple stores that are being fed from a single distribution center, which is then being fed by the manufacturer. So you can see how the whole problem channels through. So the question is, how do you minimize the number of packs that get opened at a distribution center? What are the number of packs that you should order, etc.? So the model formulation, essentially, the objective function is to minimize the total cost, which could include handling costs at the distribution center or at the store itself, or mismatched penalty cost, because if you have too much inventory, you've got the problem of markdown, or if you have too little, you have lost customer satisfaction. The main decision variables, like I mentioned, is how many packs to order from each place, etc. And the constraints, there are several business rules. And the challenge when you're building a problem that can be used by multiple different organizations or companies is that you want to make it flexible enough so that each company, each organization can put their own business rules and then go to the solution. So we need to be able to build all of that into that. So the input data, of course, are the different handling costs, the different mismatched penalty costs, and the different pre-pack configuration for whatever product you're ordering at that particular time. That's the input data. The output data, of course, are the optimal order quantities, which are typically integer valued here. You're not ordering half a shirt, right? So the number of outer packs, the number of inner packs, the number of opened inners, these are all the things that it comes out. The solution gives you all these results. And for each pack and store, how many packs need to be opened, how many can remain unopened, etc. And for each store and size, there could be number of units that are in order, etc. So there are lots of things that come out of the solution. The business rules, which I briefly mentioned, is do not order loose inner packs, do not break inner packs as much as possible. You don't want to hold excess inventory at the distribution center. You also want to have a set min-max number of outer packs of each type, the inner packs for each type, etc., etc. These are all the different business rules that you need to incorporate into the solution. The solution methodology, like I mentioned, all of these variables that you need are integer variables, so it's an integer program, but then you have a huge, huge number of constraints. It's a very, very large mixed integer problem that you want to solve. And anybody who's done optimization knows that integer programming is a very hard problem. And when you have problems of this size, it is impossible to just use a generic solver to solve it. So you have to build some custom heuristics. So it's a combination of using the solver, then fixing it, etc. So the mathematical model is MILP, Mixed Integer Linear Programming. And the other challenge is that you might need to solve different instances continuously, because you could have changes in the needs, etc., etc. And the desired response time when you're handling this for thousands of stores ends up being very, very quick response. As soon as you put in a request, you need the response very quickly. And so we needed to find heuristics to find the best solution as quickly as possible. The heuristics that we used, this was a few years ago, so now it has continued to improve as well. We call them the benchmark heuristics, where we did some ad hoc solution to figure out what the benchmarks used to be, what we have, and then do some ad hoc heuristics to figure out whether it actually meets the constraints or not, and just adjust it up and down, etc. And there's a separability heuristic, which helped us quite a bit, where we are actually the solver tells you that actually this problem can be separated out in different subgroups. And maybe you can solve the problem for specific stores separately, and instead of doing it entirely, because the problem is completely separable. And if that is the case, then you can do better by solving each store separately, and so on. So we included all these types of rules into the solution methodology. And then we had some rounding heuristics, where we solved the relaxation, the LP relaxation, and then impose some additional integer constraints, and then went back, and so keep going round and round and iterate through that to figure out. So most of this is included in some of the patents that my team got, the US patents. So there are more details in that. If you want to just look up pre-pack optimization, SAS Institute, you'll find that. So the benefit of using size optimization are you reduce the sales loss, like I mentioned. You improve profit margins because you're minimizing the costs of handling costs, etc. You're maximizing the revenue and keeping the location inventory levels as close to the size demand as possible. And of course, increasing customer loyalty. Like I mentioned, if the customer walks away because he did not get the size he wanted, he's going to be unhappy and probably not come back again. And the other thing that we learned is that as part of this solution, we can also get some preferred configurations. So we can interact with the vendor themselves and say, hey, instead of doing your pre-packs in this combination, why don't you use this? And in this case, because this will match our demand better than the ones that you currently have. So you can have some negotiation, so you can do some vendor negotiation as well. So collaboration with vendors becomes possible. And overall, you can increase the quality, improve the quality of the assortment plan. So this was just one particular optimization example in retail that I shared with you. And in general, what I'd like to leave you with is there is huge opportunity for doing such things in the current era of analytics, data science, and AI. There are plenty of opportunities. And remember always, the interdisciplinary collaboration is extremely important. And again, going back to what I said at the beginning, that the whole is greater than the sum of its parts. So with that, I'd like to again thank you very much. And one more personal thing I would like to share with you is that my daughter-in-law is a very, very loyal customer of Target. All my two grandchildren all the clothes they wear are purchased at Target. So with that, I want to say thank you very much, and have a wonderful day, and thanks.